Welcome back to this channel for practice problems for actuarial exams. We will look at a problem for exam MLC today. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. And if you would like to make a tax-deductible donation to support our students, you can go to smarturl.it/help-ISU-actuary. This is the first written answer problem from Spring 2017 exam MLC. You are using the following three-state Markov model to price an insurance product. And the states are healthy, denoted by 0, disabled, denoted by 1, and dead, denoted by 2. Of course, state 2, dead, is absorbing. Once you get there, you can't get out. And the healthy state and disabled state communicate with each other, so you can go from healthy to disabled with positive probability, and vice versa. You are also given the forces of transition from state 0 to state 1. It's actually constant force of 0.03. From state 1 to state 0, it's constant force of 0.01. From state 0 to state 2, it's 0.01 plus 0.01 t, so it's increasing with t. And from state 1 to state 2, it's 0.01 plus 0.02 t, also increasing in t and faster than for the previous one. You are also given that the product is issued to 100 healthy individuals age 40 with independent future lifetimes. The premiums are payable continuously while the insured is healthy. The product pays a continuous disability benefit at the rate of $5,000 per year while the insured is disabled, and pays a death benefit of $5,000 at the moment of death. The product has a 5-year term. No benefits are paid after 5 years. Also, no premiums are paid, but that's not clearly stated, but that's the case as well. 5 years of payments of premium maximum, nothing beyond that. Of course, the premium payment only happens when the person is healthy, but only for those 5 years. For a single policy, show that the probability that no benefits are paid during the course of the policy is 0.7 to the nearest 0.1. You should calculate the value to the nearest 0.01. Using the normal approximation with continuity correction, calculate the probability that no benefits are paid for at least 65 of the 100 policies issued. Write down Kolmogorov's forward differential equations with the associated boundary conditions for this model for the property of transition from state 0 to state 0 in time period t for a 40-year-old. The property of transition from state 0 to state 1 for a 40-year-old of a time period t, and the property of transition from state 0 to state 2 over a period of time t for a 40-year-old. Use Euler's forward method with a step size of 0.1 to calculate the expected number of insureds in the disabled state at time 0.2. That's part D. And part E says that you are also given that the force of interest is 0.05, and you are given this series of expected present values, or actuarial present values, for life insurance, but really something like life insurance. It's capital A bar. The first one is for a person that is healthy right now, there is a one-time payment at the moment of transition to state 1. The second one is for a person who is healthy right now, so big A bar, 02 in superscript. For a person who is healthy right now, that's the first superscript, a one-time payment at the moment of transition to state 2. So this is life insurance. But the first one was not. It was like a one-time disability payment at the moment the person becomes disabled. And then the third one is for a person who is disabled now, a payment at the moment of death. All three were unit payments, so unit life insurance like products. Then we have annuities. And the first one is for a person, a unit annuity for a person who is healthy now, and the payment is made while the person is healthy. So the first zero tells you the person is healthy now, and the second zero tells you that the annuity is paid while the person is healthy. And the annuity is paid continuously, and you can see that it continues only up to age 45, effectively. The second one is for a person who is healthy now, and the annuity is paid as long as the person is disabled, while the person is disabled, paid continuously. The third one is, this one is a bit strange, but, well, it's given, for a person who is healthy right now, and the annuity is paid while the person is dead. Of course, it's paid only up to age 45. Which is kind of strange to talk about a person being age 45 while the person has been dead for a while, but that's what the notation says. Next one is A bar with 10 superscript. That's for the person who is disabled right now, and the annuity is paid continuously while the person is healthy. So in state 0. The next one is A bar 11 in superscript. That's annuity for a person who is disabled right now at the beginning of when we're counting this, when we're calculating this actuarial present value A bar, little a bar. So for a person who is disabled right now, and the payment is made as long as the person is disabled. So the first one tells you the person is disabled, the second one tells you that the payment is made while the person is disabled. Next one is a continuous annuity. Upper 1-2 means that the person is disabled now, and the payment will be made during the time when the person is dead, but only up to age 45, because we start from age 40 plus k, and then we go no more than 5 minus k years after that. So we have all this data in this little table in the problem. Show that the annual net premium rate for per policy is 2,200 to the nearest 100. You should calculate the premium rate to the nearest 1. At time 3, 80 insureds are healthy, 11 are disabled, and 9 are dead. Calculate the total net premium reserve for this block of business at time 3. Okay, so the probability that no benefits are paid during the course of the policy is the probability that the person, now 40-year-old, who starts out as healthy, so in state 0, for 5 years will stay in state 0 continuously. Then only premiums are paid, no benefits are paid. That's denoted by P upper 00 with a bar above them, which indicates that the person starts out in state 0 and it ends up in state 0, but between them the person is also in state 0 continuously. That's what this bar above the 2 indicates. The person is 40 years old, that's why the subscript, and we're looking at 5 years from age 40. That's a 5 in front. Well, so what is that probability? So any probability like this where the person remains in a given state for a period of time is always calculated as e to the minus integral of the force of transition out of that state, total force of transition out of that state, which is the sum of all the forces of transition that can take the person out of the state. So mu01 plus mu02 in this case. This is very much like the calculation of probability of survival under constant force in just regular life insurance. What do you do there? You take e to the minus integral of the force. And the force of mortality is what takes that person out of the state of being alive. So this is the same thing. The total sum of these forces is the total force of transition out of state 0. Same thing, really. So that's e to the minus 0, integral from 0 to 5 of 0.04 plus 0.01 t dt. The 0.04 came from adding 0.03 and 0.01. And then we just calculate the integral of that. It's 0.04 plus 0.04 t plus 0.005 t squared. Of course, the minus in front of everything from the minus in front of the integral. And we evaluate from 0 to 5, and this ends up being e to the negative 325, or approximately 0.7225235. So that's part A. And for part B, let n be the random number of policies for which no benefits are paid. For each of 100 policies issued, no benefit is paid with probability that we just calculated, and a benefit is paid with probability 1 minus that. Thus, each policy is a form of a Bernoulli trial with a probability of success of p, and success means no benefit is paid. The random variable n then has the binomial distribution, because the sum of these individual Bernoulli trials, which count how many policies. Bernoulli trial is a success if a policy pays no benefit. And then if you're counting how many no benefit policies you have, you're basically counting how many successful Bernoulli trials you have. So that's, of course, a binomial distribution. And the parameters of this binomial distribution are p, which we just mentioned, and n equal to 100. So the mean is n times p, and the variance is n times p times 1 minus p, which we often denote by q. And a binomial distribution is a sum of independent, identically distributed random variables, Bernoulli trials, just as we saw this. So n can be approximated with a normal distribution, and the normal distribution that you use to approximate it has the same mean and variance as the thing you're approximating. So if you studied for exam P with me, you know that I call this the fake ID principle. The whole central limit theorem application that we use all the time is that if you have a sum of independent, identically distributed random variables, then you can, for a large number of those variables, you can approximate that sum with a normal distribution which has the same mean and variance as that sum. So the approximation is fake because it's with something that is not really the distribution that we're working with, but it's a pretty good approximation. However, it can't be fake too much. So when you have a fake ID, it still needs a real picture on it. It can't be a fake picture. The ID is fake, but the picture has to be of the person who wants to fake the ID. The same way, the distribution, the normal distribution, continuous normal distribution that we use to approximate, is a fake, but not too much. It has to have the same mean and variance as the thing it approximates. So it has to be sufficiently close to the truth. Just like a fake ID has to be sufficiently close to the truth so that you shouldn't do it, but if you were to do it, so that you can use it, you have to have a real picture in it. Now let us write z for the standard normal distribution and phi for its cumulative distribution function. Then the probability that n is greater than or equal to 65, which is what we're looking for, is the same as probability that n is more than 64.5. Why do we switch to 64.5? That's called continuity correction. We're approximating a discrete random variable with a continuous one. And this produces an error because the discrete random variable that assumes only integer values, you can kind of draw a histogram of it based on its probability function. Imagine that at every point, like this 65, you extend a line to the left of 65 by 1/2 to 64.5, and to the right to 65.5, and draw a rectangle standing up of height equal to the probability of hitting 65. Then the area of this rectangle is 1 times the probability of hitting 65, so it is equal to the probability of hitting 65. If you draw a rectangle like this over every point, centered at that point but going to the left and to the right by 1/2, then what you get is a form of a histogram, something like that looks like a histogram, but it kind of starts resembling a probability density function for a continuous distribution. And then you see that the count for 65 includes everything starting from 64.5, and if you want the normal distribution, which would be a line going over those through the tops of those rectangles, a curve, and the area under the curve is the probability, that whatever probability we estimate will be estimated as the area under the curve. To be precise, it has to start counting the area at the same point as the discrete distribution counts the area, and the discrete distribution starts calculating the area for n equal to 65 from 64.5 through 65.5, and then taking the height equal to the probability of hitting 65. And so that's why we switch to probability that n is more than 64.5. For the discrete distribution, it doesn't make any difference which of the two probabilities you calculate, but it is significantly different for the continuous distribution, and going from 64.5 makes the approximation significantly more precise, which is what we want. And then we subtract the mean divided by standard deviation for n, and for the right-hand side the same way. But when you do this, because n is approximately normal, the standardized version of it, standardized meaning that it has a mean of 0 and standard deviation of 1, that becomes standard normal. And in the right-hand side, we plug in the numbers. And when you plug in the numbers, you get that this is the same as probability that z is more than negative 1.731481. So if you have good visualization of what this means in terms of probabilities under the standard normal PDF curve, then you know that immediately that this is the same as probability that z is less than or equal to the positive version of this number, so z less than or equal to 1.731481. Or you can formally prove it by noticing that, well, this is the same as 1 minus the probability as z is less than or equal to this number that we have here. But phi of minus something is the same as 1 minus phi of that something. So we end up saying that this is the same as probability of z being less than 1.731481, or phi of 1.731481. And that's using either some kind of normal distribution calculator, which is now available at some actuarial exams, or just using a table that's approximately 0.9583. Now, for the Kolmogorov-Forward equation. Even though the textbook for the exam does not present a Kolmogorov-Forward equation in the matrix form, I will insist on doing that because I have a very hard time memorizing it in any other form. And on top of that, it is so easy to remember it once you write it in matrix form. I don't understand why you would do it any other way. So maybe I'm being stubborn, but here it is. To write out the Kolmogorov-Forward equation in matrix form, you write the transition matrix, which is what you see here. Of course, in this case, the bottom line, the third row of the transition matrix is 0, 0, 1. And the generator matrix, which consists of forces of transition from each state to another state, but along the diagonal where you would normally have, well, you would assume that it's a force of transition from 0 to 0, but no, it's the force of transition out of state 0 with a minus sign. Now, because in the first row, the first entry is mu 0 is the same as mu 01 plus mu 02, and then we put minus sign in front of it, the sum of the terms in the first row is 0. and it's true for every row. So this matrix is called the generator matrix, and we can plug in the values from the problem and get its form as you see here. And the Kolmogorov forward equation is says that the derivative of the transition matrix is the transition matrix times the generator matrix for the time 40 plus t, applied to 40 plus t. Okay, that's great. So we just write it out. So the derivative of the transition matrix is just the matrix of derivatives. The bottom line has constants, so all the derivatives are 0. So there are only 6 non-zero terms there. And when we multiply them out, it gets to be a little bit of work, but it's not so much. So we need to multiply out these two matrices. And this is what we get. We get 9 equations, but the last 3 are just trivial. They all say 0 equals 0. And these are the first 6. The problem asks you actually for the first 3 of these. So you're doing a little bit too much work. But it's okay if you can just use the matrix form to write out the 3 that they're asking for. That's no problem. So here are the 3 equations the problem asks about. There are the equations for 0, 0 transition, so from 0 to 0, 0 to 1, and 0 to 2. And what are the boundary conditions? The boundary conditions are pretty standard in cases like this. The boundary condition first is the probability of transition from 0 to 0 in no time, in time 0, within a time period of length 0. Well, that's 1, because you're going to stay. If you don't have any time, you're going to stay in state 0. Probability of transition to state 1 is 0 because there is no time to transition. And the probability of transition to time to state 2 is also 0. Okay, it's not so easy to solve these Kolmogorov forward equations, although, well, they are what we need to use when we calculate anything about probabilities of a system in which you can go from a state to another state and then back and then back and then back. Then you can't use any normal kind of integral of the force and then e to the, it's not going to work because there's just too many possibilities of transitions. While the Kolmogorov forward equations hold no matter how complex the system is. So that's why we use those equations. And then what do you do if you can't solve a differential equation? So this Swiss mathematician Euler came up with a very simple procedure. You have a derivative of a function in a differential equation. You don't know what to do. Well, approximate the derivative with a difference quotient. So if you have a derivative of, say, this kind of probability of transition function, it's written as a function of t, and we evaluate a derivative of a specific point s. Well, what is it going to be? It's going to be the value at s plus h minus the value at s divided by h, and then as you let h go to 0, this will be the derivative. That's a definition of a derivative. And he said, well, then this right-hand side, which in calculus we call the difference quotient, is approximately equal to the derivative. And we actually told to use a difference quotient for h equal to 0.1. Although I'm going to have a little bit of issue with the way SOA wrote out the solution because we can do this approximation immediately for the derivatives on the left-hand side of the Kolmogorov forward equation when we start at h40 and we've moved forward, but we don't have Kolmogorov forward equations at h40.1. We actually don't. We wrote them out differently, and that's what you see in what I gave you and in the SOA solution they published. So I don't agree with what they wrote out there, although it's approximately correct because a derivative you can calculate the derivative as the limit of f of x plus 2h minus f of x plus h divided by h. That will actually converge to the derivative under certain conditions. It's a nice real analysis problem of when that happens. So that's why it kind of works what they did, but it's not really correct based on what is said in the problem. Nevertheless, not the central issue here. I'll just show you what I think is reasonable in approach to this. The product was issued to 100 healthy individuals age 40, and we want to find the expected number of insureds in the disabled state at time 0.2. So we want to find the probability of going from state 0 to state 1, from starting at age 40 within 0.2 units of time. And then we multiply it by 100, because we have 100 people to start with. Okay, so we start with the first equation for transition from 0 to 0, and we take the approximation of a derivative and write out the right-hand side of the equation, of the Kolmogorov-Forward equation that we had for P00. When you do this, you use that boundary condition that P00 over time period of length 0 is 1. And then this whole thing lets you calculate the approximation of 0.1 P4000, and it comes out to be 0.996. We do the same now for transition from state 0 to state 1. Again, we plug in everything. Notice that we plug in the initial t that is in the formulas where you had parameter t time. Well, it's 0 at this point because we start out at time t equal to 0, and we calculate the derivative there. So we do the second calculation. We get an approximation of 0.1 P4001, which is 0.003. But we want to get to probability of transitioning from state 0 to state 1 starting at age 40 over 0.2 units of time, 0.2 years. And we can write that as 0.1 P4000 times 0.1 P40.101 plus 0.1 P0140 times 0.1 P40.1 upper 11, meaning that to go from state 0 to state 1, you can go from state 0 to state 0, then from state 0 to state 1, or from state 0 to state 1, and then from state 1 to state 1. Excellent. We actually calculated those probabilities relating to a period of time of length 0.1 in our first approximation where we use the Kolmogorov-Forward equations. But we actually don't have Kolmogorov-Forward equations for age 40.1. So what are we going to do? Well, we can do the work of redoing all the Kolmogorov-Forward equations. Scary stuff to do it over and over. But I think it's much more reasonable to simply say that the force of transition is defined as a derivative. And what is the meaning of the force of transition, by the way? Well, then you have to remind yourself, what is the meaning of the force of death? Or force of mortality. That's what I should have said. Force of mortality. Force of mortality, if you read my study manual, I say there, force of mortality, how do I define thee? And I list this list of formulas. And one of them is that if you multiply a force by a short period of time where this force applies, then that's roughly the probability of dying in that period of time. The same way, if you multiply the force at age 40.1 of transition from 0 to 1 by a period of time of length 0.1, then that's roughly the probability of transition from 0 to 1, starting at age 40.1, within 0.1 units of time. So that's why 0.1 P0140.1 is approximately equal to 0.1 times mu 40.1 upper 01. That's the second formula. The first one, though, is about not dying, but staying where you are. Well, if the probability of dying is little h times the force, then probability of staying where you are is 1 minus that. And what is the total force of getting out of state 0? It's mu upper 0. Sometimes written with a dot after the 0. So I didn't write it that way, but if you see mu upper 0 dot, that with a little dot after the 0, that means the same thing. Okay, and then if you write those two approximate equations, plug in the forces at the age 40.1, you get approximations of those two probabilities, which are missing in the formula just above, but we just got them this way. So we plug them in and we get our approximation. As a result, it's 0.0059784, and the expected number of disabled insureds is 100 times that, 0.9784. Okay, now let us write P for the annual net premium, or benefit premium. Premium paying only for benefits, and it's payable as a level annuity. Note that the premiums are payable continuously while the insured is healthy, and the insured starts out as healthy. So the expected present value, or actuarial present value, of the premiums at the beginning is P times actuarial present value of a continuous annuity issued to a 40-year-old only over the next 5 years. That's 40 colon angle 5. And at the top, the superscript says the annuity starts in state 0, so when the person is healthy, and is payable while the person is in state 0, so while the person is healthy. Well, that's exactly how the premium is paid. So that annuity is given in that little table of values that comes in the problem. We look it up, and it's 3.887p. Then the expected present value of the death benefit is 50,000 times, and what is this? Big A bar, 40 colon angle 5, upper 02. Well, it's a continuous form of payment. So at the moment of death, not really death, but transition from state 0 to state 2. So the person starts out in state 0, and the moment the person transitions to state 2, there's a payment made. That's the death benefit in this. The value of this A bar upper 02 is given in the little table that comes with the problem. It's 0.146. We plug it in and we get 7,300. Then the expected present value of the disability benefit is 5,000 A bar 40 colon angle 5 01. That's an annuity that is paid to somebody continuously, to somebody who starts out healthy. That's the first superscript 0. And the second superscript 1 tells you that the annuity is payable as long as the person is disabled. Well, that's exactly how the disability benefit is paid. So that's what this means. And that annuity value is given in the problem. It's 0.262. So we plug it in, multiply it by 5,000, we get 1,310. So the premium is simply equal to the ratio of actuarial present value of benefits, which we just calculated, 7,300 plus 1,310, divided by the actuarial present value of a level annuity that is paid, unit level annuity that is paid the way premium is paid. You know this principle from basic life contingencies premium calculations. It's the same idea. This comes out to be 2215.08, and of course that's 2,200 to the nearest 100. Okay, at time 3, 80 insureds are healthy, 11 are disabled, and 9 are dead. We now calculate the total net premium reserve for this block of business at time 3. I want you to notice one obvious but kind of important thing. The reserve will be only held for the healthy lives and for disabled lives. No reserve for the dead. Why? Because when an insured is dead, there are no benefits payable in the future for that person, and you only keep the reserve for the purpose of paying benefits. Okay, for a single healthy life, the reserve is the actuarial present value of future benefits minus actuarial present value of future premiums. just like what you learned in basic life contingencies. And that's 50,000 times A bar 43 colon angle 2 02. So the person is now 43, this is time 3, 2 more years remaining of the policy. The death benefit is paid at the moment of death, and it's 50,000. That's why big A for single payment, death benefit, and bar above it because it's paid continuously. And then 02, you need to pay attention to the meaning of that. That means that the person starts out healthy, and 2 means that the payment is made the moment the person transitions to state 2. Now, of course, state 2 is absorbing, so there is no transition anymore. That's it. Plus, the disability benefit is just annuity of 5,000 paid, well, how? While the person is disabled. And this is continuous annuity, so A bar. The person is 43, 2 more years are remaining. The person starts out as healthy, that's why the superscript of 0, and the annuity is payable as long as the person is disabled. That's the 1 superscript. Minus the premium, which is paid as a continuous annuity, right? The person is now 43, 2 more years, and the annuity is paid in such a way that the person is now healthy, and the payment will happen in the future while the person is healthy. Notice that it doesn't say that it has to be healthy continuously without any interruption. The problem does not say that. The problem says the premium is paid while the person is healthy without any conditions. So if the person becomes disabled, then comes back to healthy, then the person has to start paying premiums again, even though the person is not required to pay the premium while the person is disabled. So all of these life insurance and annuity factors values are given in the problem in a little table with data. We plug them in, and we get what you see here, which is 935.95. Then the reserve for disabled life, one of single life, is well, 50,000 death benefit, and you can see that 1, 2 superscript indicate that the person is disabled now, and the payment is made when the moment the person transitions into state 2. So the person goes into the state of being dead. And then 5,000 annuity payable, well, continues, but 1, that means that the person is disabled now, and the payment will continue as long as the person is in the state of being disabled. Minus the premium payment, which is also an annuity, but now look, it says 10 in the superscript, which means that the person is disabled now, and the payment will happen as long as the person is healthy in the future. So while the person is healthy. So the person has to transition first to state of being healthy before any payment is made of this premium for the policy. All of these life insurance annuity factors, again, are given in that little table of data. We plug them in. We get 16,462.34. And the total reserve is the sum of all 80 healthy lives reserves and 11 disabled lives reserves. So it's 80 times the first reserve we calculated plus 11 times the second. Plug in the numbers, we get the answer of 255,962. Please remember this is copyrighted material, and problems from past Society of Actuaries examinations are copyrighted by Society of Actuaries and are used here with permission.